Welcome to the short discussion on the topic finding support reactions in cantilever beams. This is a topic in shear force and bending moment in beams. It is a part of syllabus in strength of materials 1 course, right? So basically, we are trying to look at how to find the reactions for different kind of loadings that are acting on a cantilever beam, right? So our target is how to apply the equilibrium equations, right? Because equilibrium equations are alone sufficient. We don't need any endeavor because cantilever beams, simply supported beams, these are determinate structures, which means by definition the number of equilibrium equations are sufficient enough to find all the unknown reactions of the supports of the beam, right? So basically our target is how to apply the equilibrium equations to find the support reactions in cantilever beams if only point loads are there, right? Or if maybe some other combined loading system is available, how to apply these equilibrium equations. If you know how to apply equilibrium equations regardless of whatever the loading is available, you can easily find out the reactions, right? So before going to that, let us have a little understanding about the equilibrium equations. In engineering mechanics, we have studied that for a rigid body in static equilibrium, for the body to be in equilibrium, these conditions are sufficient and required, right? They are necessary and sufficient conditions, right, for a static equilibrium. Right? What are those? The force is acting in all the directions, say sigma fx, sigma fy and sigma fz must be equal to 0. The moment at any particular point must be also be 0. So there are, if you are taking a three-dimensional problem, there will be 6 number of equilibrium equations, 3 from the force equilibrium, 3 from the moment equilibrium, sigma fx, sigma fy, sigma fz and mx, my, mz. But for a two-dimensional state of stress or equilibrium, you require only 3 equations, that is sigma fx, sigma fy and sigma mz. Okay, if these equations are no, if you are able to use these equations effectively, doesn't matter whatever may be the loading acting on the beam, you can easily find out the reactions of the supports, right? So let's look at some simple loading. So for all kinds of reactions, you don't need much endeavor. Just within 2 steps, 2 simple steps, we can solve this. Okay, what are those? There is a cantilever. We take to illustrate that. Let us take a simple example. There is a fixed support here, and other side is free. Therefore, it is called a cantilever beam. So he is asking the support reactions, right, of a cantilever beam. So cantilever beam has only one support, that is fixed support. And what are the, we have already in the previous section we had this knowledge of marking the reaction component, the supports. A fixed support, right, you have to mark the reaction components. Fixed support can offer all 3 kinds of resistances, like vertical direction, horizontal direction and rotation, right? So it has resistance to all 3 directions. So let us mark. So one may ask, sir, why you have marked upwards? You doesn't matter. You can even take downwards, doesn't matter. Or you can take his left, and you can even take this one as a counterclockwise direction. Here it was marked direct, right? So then the other question is, if somebody marked like this, somebody else marked in a different way, whether they get the same answers? Yes, they will get the same answer, because your magnitude doesn't change. If at all your direction assumed is not correct, then what will happen is, probably what will happen is, you will get a negative sign in our magnitude, right, in our no solution, right? So based on that, you can later on revert back to the actual direction, right? So first you have to mark the no reaction components. Doesn't matter whether you have taken no vertically upwards or downwards, doesn't matter, but you have to mark one reaction in the vertical direction, one reaction in the horizontal direction and one reaction in the moment direction, that is z direction, that is moment component. If you mark this, so The two steps only I am going to discuss here. With that we can get the solution. The first step is idealize the loads and mark all the reaction components. In this case, because the loading is very straightforward, no, all concentrated load, we don't have to make any idealization. This itself is an idealization. Okay, idealization in the sense, when there are any other loads other than point loads, you should make them convert, or you can convert them into a point load. Right? What are the other types of load? Maybe a uniformly distributed load or many uniformly varying load. You should convert them into a what you call concentrated load, a point load. Then you can start. Right? So you have to idealize the loads and then mark all the components. So for a fixed support, now we marked, right, a vertical reaction upwards is an assumption, remember, right, and horizontally right side we have kept, and there is a moment like this. After marking this, right, you can simply, the next step is right, no, in the sense, you know that through, as I said earlier, only equilibrium equations apply, you will get the solution. So the second step is, what is the second step? Then it will be simply application of the equilibrium equation. So you can apply the equilibrium equation, right? So in the equilibrium, while applying the equilibrium equations, you should look at the no, given problem. As long as there is no inclined loading system or horizontal loads acting on that, Fx equation has no significance at all. That's why in beams most of the times the loading will be vertical, and we don't use sigma Fx equation. Something around 95% we don't use it. Only when there are inclined loads are acting, or then some kind of horizontal loads placed on the beam, then only we can refer to sigma Fx equation. So the two common equations that are generally used is sigma Fy equal to 0 and sigma Mz at a specific point. It doesn't matter, only A you have to take. Wherever you want, you can apply the moment. Okay, so sigma Fy equal to 0 if you apply. So when you are applying this particular equation, right, sigma, you should always know, before applying itself there must be some what you call sign convention, you have to write it, right, such as whether you are going to take upward positive or downward positive, right, that you have to decide which direction you have to take. So one may ask whether no, either way take, somebody may take downward positive, somebody else may take upward positive. It doesn't matter what way you take, because equal to 0 is there, your solution will be always same. Regardless what way you take, no, your answer or solution doesn't differ. Okay, so for example here, temporarily what I am doing is I am taking the upwards positive, right, and downwards negative. So with that we can proceed. So if you look at that in our diagram here, what we are having, what are the upward forces acting? There is only Va, nothing else. So Va is plus Va, rest of the things are negative, minus 10, minus 20, minus 10, minus 10. So we are referring to vertical direction only, remember. So vertical direction, no other forces. Upward forces are only one, that is Va. So plus Va, minus 10, minus 20, minus 10. That's what written here. Plus Va, minus 10, minus 20, minus 10. So Va equal to 40. Okay. Then Mz at A, right? The other equation you can write anywhere, right? So Mz at equation you can apply at the support A, because I require no, at the point A only, the moment, because all three is required. As I told you, unless there is an inclined loading and horizontal loading, HA is always 0. You don't have to bother about this. Straight away put it 0. If there is no horizontal loading on it, if there is no inclined load acting on it, straight away put HA to 0, because there is it doesn't develop resistance. When will it come? When there is a loading acting on that. There is no loading in the horizontal direction, then what is the meaning of HA? Right? Next, MA you want, right? So you want MA. For MA, what you do is you take a moment at the point A. Here also you have to, you should stand at the point A and look at, right? So what are the clockwise direction? Here also one direction you have to take positive, another direction as negative, right? As I told you, which direction you take positive, it doesn't matter, because equal to 0 is there. Ultimately your solution will be not varying, right? So if I take clockwise positive, right? Then I will put wherever clockwise movements come plus, otherwise it is negative, right? So now look at this. I am standing at the point A, right? Moment is nothing but force times distance, right? So how many forces are there? One, two, three. Three forces will be causing moment, and VA force is not causing moment because I am standing at A. Where is the perpendicular distance for it to cause moment? So VA will not create any moment. MA is directly moment, so I have to take that. So MA is acting in what direction? You are here, right? So to the point A, we have to consider all these directions. So I am at A. This is A, my A point. So for A point, right, this is what direction? Clockwise. So MA will be positive. Whereas, what about this? No. Is it clockwise or is this anti-clockwise? Sorry. You see, this is the direct. Sorry, what direction we have written here is yeah, it is a clockwise direction, right? You look at it, clockwise direction, and these are also clockwise, right? 10, 20 towards A, you have to check it, right? This is the direction, this is the direction, this is the direction. Okay, so here doesn't matter whether you take no clockwise or anti-clockwise. Later on, based on the sign you got, whether the direction is correct or not, you can identify, right? So here, of course, because it is minus, we can put minus MA. Okay, and what direction it is? This is clockwise. So clockwise, that's why it is yeah, sorry, clockwise. Therefore it is positive. We don't have to put negative, right? All are positive only. MA positive, 10 times 2 is positive, 20 times 2 is also positive, 10 times 2 also positive, all positive. So you got MA equal to minus 160. Now after getting this, finally you can represent. Here you got a negative. That means the assumed, what is the meaning of this negative is, your assumed direction of MA is not correct. So that means you reverse it. What was taken direction? We have taken in clockwise, but it's supposed to be anti-clockwise. Okay, that's the only meaning, nothing else. So after getting everything, you just represent it, all the reactions. Then it is complete. So we have HA0, we got it. MA, we have 160 we got. But the direction originally assumed is this way. But we got negative, therefore it should be reverted. So you should keep in anti-clockwise direction at the point A. And then VA we got plus 40, so represent as it is 40. Okay. Now here after getting, it is always make a a kind of check whether you have done it correctly or not, right? It is simple equation, but the procedure I am telling, we don't have to even use with simple common sense one can say that no, these reactions or summation of the downward forces must be up balanced by the downward. So for 10 plus 20 plus 10 40, this is straight 40, right? So but still this will help us to solve typical type of problems. When you follow the procedure, that will help us in even when the calculations are little complex, right? So HA0, because no horizontal forces are, this equilibrium equation we should check, that's at the end. So no forces now, that means HA0 is correct. Similarly, vertical equilibrium 10 20 10, so 30 40, so 40, so that balanced, and then this is 160, right? So you can calculate the moment due to all these and equate to this. They should be equal. 10 times 2 20, 20 times 2 40, so 20 plus 40, right, 60, and then 10 times no 10 times 2 20 times 4, because the distance to A is 4. So 10 times 2 is 20, 20 times 4 is 80. So 20 plus 80, 100, and last one 10 times 6. Okay, so you got 60, already 100, so 160, so balanced. So you should always check after finding some, because there is a chance to commit mistake. At the end you can always make a check of that. Now you take little no kind of complex or you can say combined loading for a cantilever beam. Try to see how to find using the same two steps. You can find out the reactions. Let us look at that. It's very simple. We have a loading here, is a cantilever beam. Here three different types of loadings. One concentrated load, one couple was given, one UDL was given, right? So we can apply this two steps, right? First step is idealization of the loads. What did I tell you? Idealize the load means you should represent whatever may be the loading given on the beam. You should convert them into a point loads, right? So here couple you don't have to convert into point load, right? So this is already point load. We don't have to do anything. But UDL immediately convert into a point load. How to do that? So you should always for a UDL just find the area of the UDL or distance, in the sense the intensity you multiply the distance over which it is acting and exactly place at the center. Okay, so it is a symmetrical load, it always acts at the center. So 4 times 2 8. Now you are ready to apply the equilibrium equations. Of course support reactions you have to mark. As I told you earlier, fixed support you mark the 3 reactions. Out of 3, one is invalid, right? In the sense it is 0, you don't have to write HD, you don't have to write. As I mentioned no just now, unless there are horizontal loads acting on the beam, or even the inclined loads acting on the beam, there is no meaning of HD, right? So you can put HD 0 straight away, apply the other two equations, that is Fy equal to 0 equation, which means you have to use the sign convention. So upwards positive, downwards negative. As I said earlier, it doesn't matter, you can even take downwards positive, upwards negative, but you still you get the same solution. Okay, so VD you have to assumed upwards, so VD plus and minus 2 is one concentrated moment does not come. This is a moment should not be brought into Fy, right? Y direction forces only we are using 2 and 4 times 2, that is 8. So you got a VD straight away value. Then go to the next one, use the other equilibrium equation. Only 2 is sufficient. As I told, 2 unknowns, 2 equations are sufficient, don't go for third one. HD directly by looking at no inclined loads, no horizontal loads, HD will be 0. Okay, next you have another equation. So you take moment about the point D. So when you take moment about the point D, what loads come into picture? There is one moment here, this will come into picture. This 2 also causes moment. This is the whole perpendicular distance for the 2 load. That means 2 times 1 into 2 into 1 plus 2 plus 1, that is 4. 2 times 4. Right? This is in what direction? This is in the anti-clockwise. This is also in the anti-clockwise direction. Similarly, this 4 times 2, 8 kilonewton also causing moment at the point D. So 8 times, what is the distance? This is total 2, that means this acting at the center, that means this is 1 meter. So this one, we want the distance as a 2D, because is very important. Where we are taking moment is important. This is the point where we are taking moment. So distance of the load to the point, this point only we have to measure. So 1 plus 1, 2. So that is 8 times 2, that is 16, right? So what we got now? 2 and acting in the anti-clockwise. So let us say anti-clockwise is negative, because right in the beginning we have to make that decision whether which one you are taking, positive or negative. Don't take both negative or both positive, that is wrong. Your choice is there, you can assume clockwise while for only equilibrium equation you can take either clockwise positive or anti-clockwise positive, doesn't matter. I assumed clockwise is positive, anti-clockwise is negative. Let's start now. Sigma mz at the point D equal to 0. So md, there is a moment at the point D, so let us write that first. Md is in the which direction? Md is in the clockwise, so that should be positive, and the rest of all 2 is a moment acting in the anti-clockwise direction, and then there is another load 2 times what is the total distance? 2 times this point load, 2 into 1 plus 2 plus 1, that means 4. 2 times 4, right? This is 2 times 4, this is not 24, sorry. 2 times 4 and then 4 times 2, that what is that UDL which was converted to point load, where at what distance? At 2 meters distance it is acting. Now you simplify that. 2 plus 8 plus 8 into 2, 16, right? So 18, what is this, you got 8 into 2, 16. 16 plus 8 24, 24 plus 2 26, that's the moment. And you got positive, that means assumed direction is correct. And after getting all the reactions, you can simply mark them. Only two reactions are there. VD is 10, mark it, and MD as 26. That's it. So the essence of this particular discussion is, if you know how to apply the equilibrium equations, then regardless of whatever may be the loading, you can able to solve the reactions. Just follow these two steps: idealization of the loading given on the beam and marking the support reactions, and simply apply the equilibrium equation. That's all. Thank you.